In the northern quarries of Aswan, where the Nile begins its long bend toward the sea, there is a stone that has not moved in 3,500 years. It lies in a trench of its own making, a trench carved by human hands into the living granite of the earth, and it waits there still, not because it was forgotten, but because it was abandoned. This is the unfinished obelisk, the largest single block of worked stone from the ancient world, and it is cracked. The crack runs deep into the pink-grey flesh of the granite, a fissure that appeared sometime during the reign of Hatshepsut, sometime in the 15th century before the Common Era, when the workers who had been pounding at this stone for months, perhaps years, saw the floor open beneath their tools and knew that their labour was finished. Not complete. Finished. The crack meant the stone would never stand. It would never leave the quarry. It would never be dressed and polished and inscribed with the names of gods and kings. It would lie here in its trench, in its bed, until the quarry filled with sand and the workers went home, and the centuries turned and the empires rose and fell and rose again, and still the stone would not move. It has not moved. Walk into this quarry today and you are walking into an interrupted sentence. The grammatical structure is visible, the subject, the verb, the beginning of a predicate, but the meaning hangs suspended, unresolved, waiting for a completion that will never come. Every chisel groove is still there. Every mark left by the dolerite pounders that the workers swung against the granite is preserved exactly as they left it when they set down their tools and walked away. The red ochre lines that the master masons painted to guide the shaping of the obelisk are still visible on the surface of the stone, faded by millennia of sun but legible, readable, as clear a set of instructions as any blueprint drawn by any architect in any age. The trenches that the workers carved to isolate the block from the bedrock are still open, their walls rounded and bulging with the marks of percussion, each bulge a record of a swing, a blow, a moment of human effort frozen in stone. This is what makes the unfinished obelisk the most important archaeological site in the study of ancient stoneworking. Not because it succeeded, but because it failed. A finished obelisk tells you what the ancient Egyptians wanted you to see: the polished surface, the perfect geometry, the hieroglyphic text proclaiming the glory of Amun-Ra and the eternal name of the pharaoh. A finished obelisk is a performance, a presentation, a public face. But an unfinished obelisk tells you everything the finished version would have hidden. It shows you the process, it shows you the labour, it shows you the technology, the logistics, the organisation, the limits of what was possible and the moment when possibility ran out. Had this obelisk been completed, it would have weighed approximately 1,068 tons. Some estimates place the figure closer to 190 tons, but the variance hardly matters. These are numbers that belong to a different category of mass than anything we encounter in ordinary life. A ton is 1,000 kilograms. 1,100 tons is the weight of a locomotive. It is the weight of a small building. It is a weight that modern cranes can lift in theory, under ideal conditions, with extensive preparation and engineering support. But it is not a weight that any crane can simply pick up and move across a landscape, down a river, up a ramp, and onto a pedestal. And yet the ancient Egyptians did exactly this repeatedly, with obelisks only slightly smaller than this abandoned giant. The unfinished obelisk would have stood, if it had ever stood, approximately 41.75 metres tall, nearly 137 feet, a needle of stone taller than a 12-storey building, taller than the Statue of Liberty from toe to torch. It would have been the largest obelisk ever erected, the crowning achievement of a tradition that had been developing for over 1,000 years, a monument so massive that it would have dwarfed every other obelisk in Egypt, and it would have been, in all likelihood, dedicated to the sun god Amun-Ra and to the glory of Hatshepsut herself, the woman who ruled Egypt as pharaoh, in a time when such a thing was not supposed to be possible. Hatshepsut. Even her name carries weight. It means foremost of noble ladies, and she was foremost in more ways than one. The fifth pharaoh of the 18th dynasty, the daughter of Thutmose I, the wife and half-sister of Thutmose II, and after his death, the regent for her stepson Thutmose III, who was still a child when his father died. She was supposed to rule in his name until he came of age. She was supposed to step aside when he was ready to take the throne. Instead, she took the throne herself. She had herself crowned pharaoh. She wore the ceremonial beard. She had herself depicted in the poses and with the attributes of a king, and she ruled Egypt for over 2 decades, presiding over one of the most prosperous and peaceful periods in Egyptian history. The unfinished obelisk was probably hers. We cannot know for certain. The crack appeared before any dedicatory inscription could be carved, but the circumstantial evidence points to Hatshepsut. She had a particular fondness for obelisks. She erected 2 enormous obelisks at the Temple of Karnak, and on their surfaces she had inscribed her own account of the labour required to quarry them, transport them, and raise them. "My heart directed me to make for him 2 obelisks of electrum," she wrote, referring to Amun-Ra, whose points mingle with the sky in the august colonnade between the 2 great pylons of the king. She was proud of her obelisks. She wanted posterity to know what she had accomplished, and so she left us a record, partial, propagandistic, but still a record, of what it took to move a mountain. But the unfinished obelisk tells us more. The inscriptions on Hatshepsut's standing obelisks tell us what she wanted us to believe. The abandoned stone in the quarry tells us what actually happened. The decisions, the techniques, the failures, the limits. It tells us because it was never cleaned up, never smoothed over, never polished into a presentable form. It tells us because it was left exactly as it was on the day the workers stopped working. Reginald Engelbach understood this. In 1922, the British Egyptologist conducted a detailed study of the Aswan quarries, and his analysis of the unfinished obelisk became the foundation for everything we know about ancient Egyptian stone quarrying. Engelbach measured the trenches. He measured the marks left by the dolerite pounders. He measured the width of the working channels, approximately 60 centimetres, just wide enough for a worker to kneel or squat while swinging a stone ball against the granite face. He documented the red ochre guidelines, the traces of worker organisation, the systematic grid that the ancient engineers had laid out to ensure that the obelisk would be shaped correctly as it was freed from the bedrock. What Engelbach found was not magic. It was not lost technology. It was not the intervention of aliens or Atlanteans or any of the other fantasies that have accreted around the pyramids and obelisks of Egypt like barnacles on a shipwreck. What he found was labour. Organised, systematic, patient, brutally repetitive labour. The granite of Aswan is one of the hardest stones on earth. It cannot be cut with copper tools, and in the time of Hatshepsut the Egyptians did not have iron. They had bronze, which is harder than copper but still softer than granite, and so they used the only tool hard enough to work the stone, more stone, dolerite, a dense, dark, igneous rock that is slightly harder than granite, hard enough to shatter the crystalline structure of the Aswan pink when struck with sufficient force. The dolerite pounders are still scattered in the quarry, some of them weighing as much as 5 or 6 kilograms, rounded into rough spheres by the impacts they absorbed. Workers would grip these stone balls with both hands and swing them down against the granite face, again and again, hour after hour, day after day, month after month. Each blow would shatter a few grains of granite. Each blow would deepen the trench by a fraction of a millimetre. Each blow would bring the obelisk fractionally closer to freedom. And each blow would wear down the dolerite pounder, rounding its edges, smoothing its surface, until it became too small or too irregular to use effectively, and was discarded in favour of a fresh stone. This is the technology. This is the method. This is the answer to the question, how did they carve it? And the answer is that they did not carve it at all, not in the way we use the word. They pounded it, they battered it, they pulverised it, grain by grain, with nothing but stone and muscle and time. And when you understand this, when you truly absorb the implications of it, you begin to understand something else as well. You begin to understand why the Egyptians built what they built. You begin to understand that a civilization capable of this kind of patience, this kind of coordination, this kind of long-term collective effort, was capable of almost anything. The quarry was not a place of chaos. It was a place of extraordinary order. The red ochre lines tell us this. They were painted by master masons who understood geometry, who understood proportion, who understood the shape that the finished obelisk would take, and worked backward from that shape to calculate exactly how much granite needed to be removed, and exactly where the trenches needed to be cut. The trenches themselves were not rough approximations. They were precise, systematic, designed to isolate the obelisk from the surrounding bedrock while leaving enough granite beneath it to support its weight until the moment of extraction. The workers were not slaves, as Hollywood has so often imagined. They were organised into gangs with names and foremen, gangs that competed with each other for rations and prestige, gangs that recorded their sick days and their work quotas and their achievements on the walls of the quarry itself. And yet, for all this organisation, for all this skill, for all this labour, the crack appeared. Somewhere deep in the granite, invisible to the workers who were pounding at the surface, there was a flaw, a seam, a weakness in the crystalline structure that the ancient engineers could not have detected until it was too late. And when their tools reached that weakness, when the accumulated stress of thousands of blows finally found the path of least resistance, the crack opened and everything stopped. We do not know how long the workers had been labouring when the crack appeared. We do not know how many months or years of effort were lost in that moment. We do not know what Hatshepsut said when she received the news, or whether she ordered a new obelisk to be started in a different part of the quarry, or whether she simply accepted the loss and moved on to other projects. What we know is that the workers put down their tools. They walked away. They did not come back. And the obelisk has been lying in its trench ever since, a monument to everything that can go wrong, a textbook of technique written in the language of failure. In 1979, the quarry and the unfinished obelisk were inscribed on the UNESCO World Heritage List. The designation recognised what Engelbach had understood half a century earlier, that this abandoned stone is more valuable than any finished monument because it preserves what finished monuments destroy. It preserves the process, it preserves the labour, it preserves the human hands that shaped it and the human error that stopped them. Walk through the quarry today and you are walking through a workshop that closed 35 centuries ago, and everything is still where the workers left it. The dolerite pounders, the red ochre lines, the rounded trenches, the obelisk itself cracked and abandoned and irreplaceable. This is where our documentary begins, not with a triumph, but with a failure. Not with a stone that was raised, but with a stone that never left the ground. Because the unfinished obelisk teaches us something that no finished obelisk can teach. It teaches us the questions. How did they quarry these stones? The unfinished obelisk answers that. How did they shape them? The ochre guidelines answer that. How did they organise the labour? The worker graffiti and the trench marks answer that. But how did they move them? How did they transport 1,000 tons of granite from the quarry to the river to the temple? How did they lift that weight and stand it upright and hold it in place while they slid the pedestal beneath it? The unfinished obelisk cannot answer these questions because it never moved, and yet its brothers and sisters, the obelisks that were finished, that were transported, that were raised, stand in temple complexes and city squares across 2 continents, silent witnesses to a technology we have lost and have never fully recovered. To understand what the Egyptians accomplished, we must look beyond Aswan. We must survey the full cast of giants, the obelisks and monoliths that made it out of their quarries and into the world. And we must ask ourselves a question that the stones themselves seem to be asking. Why did so many of them fall? Fly north and east from Aswan, across the Red Sea and the Gulf of Aden, over the highlands of Ethiopia to the ancient city of Axum, and you will find another field of giants. The stelae of Axum are not Egyptian. They are not made of granite. They are carved from phonolite, a dense volcanic stone, and they are not smooth-sided obelisks but elaborately decorated monuments, their surfaces carved to represent the facades of multi-storey buildings, doors, windows, beam ends, all rendered in stone, a kind of architectural trompe-l'oeil frozen in rock. The largest of these stelae once stood over 24 metres tall and weighed approximately 160 tons, and for 16 centuries it dominated the landscape of this Ethiopian holy city, a monument to the Aksumite kings who had ruled one of the great trading empires of the ancient world. Then it fell. At some point in the distant past, the exact date is lost, the great stele toppled and shattered, and for centuries it lay in pieces at the base of the hill where it had once stood. And when Benito Mussolini's Italian forces invaded Ethiopia in 1935, they saw an opportunity. They dismantled the broken stele, cut it into sections, and shipped it to Rome, where it was re-erected near the Circus Maximus as a trophy of colonial conquest. For 70 years, this Ethiopian monument stood on Italian soil, a symbol of everything that empire takes and refuses to return, but empires end. In 2005, after decades of negotiation and diplomatic pressure, the Italian government agreed to return the stele. The sections were loaded onto aircraft. the largest airlift of a single artefact in history, and flown back to Axum. And on the 4th of September 2008, the obelisk of Axum was unveiled in its original home, reassembled for the first time since Mussolini's engineers had cut it apart. The return of the Axum obelisk is a story of cultural restitution, of justice delayed but finally delivered, but it is also a story about weight. The engineers who dismantled the stele in 1937 had access to industrial cranes, motorised transport, and all the logistical support of a modern military occupation. The engineers who reassembled it in 2008 had even more sophisticated equipment, and still the task was immense. Still the logistics were staggering. Still the question hung in the air. How did the Axumites do this in the 4th century with nothing but human and animal muscle? The stele field at Axum contains many monoliths, not just the famous obelisk. Some still stand. Some never stood at all. They lie where they fell during erection, victims of some miscalculation, some failure of rigging or balance, some moment when 160 tons of phonolite decided to obey gravity rather than the will of the workers trying to raise it. The field is littered with failures. It is littered with ambition that exceeded capability, with stones that were quarried and shaped and transported to the erection site, only to collapse at the final moment. The Axumites were not incompetent. They raised many stele successfully. But the margin for error was razor thin, and when they made mistakes, the evidence of those mistakes survived for millennia. Why did so many fall? This is the question the stele field asks. This is the question that will haunt us throughout this documentary, because the Ethiopian giants are not alone in their failure. Across the ancient world, wherever megalithic monuments were raised, the record includes a catalogue of disasters: stones that cracked in the quarry, stones that sank in transit, stones that toppled during erection, stones that stood for centuries and then fell to earthquakes, to neglect, to the slow grinding of time. The ambition was extraordinary, the accomplishment was extraordinary. But the rate of failure was also extraordinary, and we tend to forget this because the failures are less visible, less celebrated, less interesting to us than the triumphs. Fly west from Axum, back across the Mediterranean, and you will come to Rome. In the piazza beside the Basilica of San Giovanni in Laterano, there stands an obelisk that is taller than any other ancient obelisk in the world. The Lateran obelisk rises 32 metres into the Roman sky, a needle of red granite that was cut from the Aswan quarries more than 3,000 years ago in the reign of Thutmose III, one of the greatest warrior pharaohs of the New Kingdom. Thutmose III conquered an empire that stretched from the fourth cataract of the Nile to the banks of the Euphrates, and he commissioned this obelisk to stand at the Temple of Karnak as a monument to his victories and his devotion to Amun-Ra. But the obelisk was not finished in his lifetime. An inscription on its surface tells us that it lay for a total of 35 years on its side at Karnak before his grandson, Thutmose IV, finally completed the work and raised it. 35 years, a generation and a half. Why the delay? We do not know. Perhaps the pharaoh died before the logistics could be arranged. Perhaps the effort required to move and raise a stone of this magnitude was so immense that it could only be undertaken during periods of exceptional prosperity and stability. Perhaps there were other priorities, wars, building projects, administrative crises, that pushed the obelisk to the back of the queue. What we know is that even for the Egyptians, even for the civilization that invented the obelisk and perfected the art of raising it, this was not a trivial undertaking. This was a project that took decades to complete. And then, 1,000 years after Thutmose IV raised it, the obelisk was moved again. The Roman Emperor Constantius II wanted it for his capital. He ordered it dismantled at Karnak, shipped down the Nile to Alexandria, loaded onto a specially constructed barge, and transported across the Mediterranean to Rome. The journey took years. The logistics were staggering. A purpose-built ship had to be constructed to carry the weight, one of the largest vessels of the ancient world, with 300 oarsmen to propel it. When the obelisk finally arrived in Rome in 357 CE, it was dragged through the streets to the Circus Maximus and raised again, a trophy of Egyptian antiquity transplanted to the heart of the Roman Empire. But even Rome could not keep the Lateran obelisk standing forever. At some point during the medieval period, the obelisk collapsed. It may have been an earthquake, it may have been neglect, it may have been deliberate destruction by Christians, who saw the pagan monument as an affront to their faith. Whatever the cause, the obelisk fell, and when it was re-erected in the 16th century by Pope Sixtus V, it was 4 meters shorter than it had been originally. The original tip had shattered. The weight that had once been 413 tons was now approximately 300 tons. And even this reduced mass required the combined engineering genius of the Renaissance, hundreds of workers, an elaborate system of ropes and pulleys and wooden towers, and months of preparation. The Lateran obelisk is the tallest ancient obelisk still standing, but it is not the same obelisk that Thutmose III commissioned. It is shorter, it is lighter, it has been moved 3 times and fallen at least once, and each time it moved or fell something was lost, a few meters of height, a few tons of weight, a few hieroglyphs of inscription. The stone is still magnificent. The stone is still one of the wonders of the ancient world. But the stone is also a survivor, a remnant, a fraction of what it once was. The Karnak temple complex where the Lateran obelisk originally stood is a forest of such remnants. Walk through Karnak today and you will see obelisks standing and obelisks fallen, obelisks intact and obelisks shattered, obelisks that have survived 3,000 years, and obelisks that did not survive the first earthquake or the first flood or the first conquering army. The record of triumph is also a record of loss. The record of success is also a record of failure, and both records are written in the same language, the language of stone, the language of weight, the language of gravity and ambition and the limits of human power. There were twin obelisks at Karnak once, a pair of monoliths raised to stand before one of the great pylons of the temple. One of them was the Lateran obelisk, the stone that Constantius II would one day steal for Rome. The other was its twin, a matching needle of granite cut from the same quarry, shaped by the same workers, raised by the same engineers. What happened to the twin? The historical record is unclear. At some point, it fell. At some point, it shattered. Whether it was earthquake or neglect or deliberate demolition, the twin is gone, reduced to fragments that were carted away or buried or lost. The Lateran obelisk survives in Rome because it was stolen. Its twin did not survive in Egypt because it was left behind. This is the pattern. This is what the stones are telling us. The obelisks that survived are not necessarily the largest or the most magnificent. They are the ones that were moved again and again by emperors and popes and engineers who cared enough or coveted enough to keep them standing. The obelisks that were left in place, left to the mercy of time and earthquake and neglect, often fell. They often shattered. They were often lost. The great irony of the ancient obelisks is that the ones we can still see are the ones that were stolen, transplanted, colonized, removed from their original contexts and placed in new ones. The ones that stayed home often did not survive. Now return with me to the quarries. Not to Aswan this time, but to a different quarry, on a different continent, in a different empire. Fly north and east from Rome, across the Alps and the valleys of Lebanon, to the ruins of Baalbek, the Roman temple complex that was once the largest religious sanctuary in the Western world. And in the quarry above Baalbek, still lying in its cut, still attached to the bedrock, still waiting for a transport that never came, there is a stone they call the Stone of the Pregnant Woman. The name is Arabic, Hajar el-Hibla, and its origins are lost in folklore. Some say a pregnant woman deceived the jinn into moving the stone. Some say the stone was left behind when the jinn fled. Some say the name refers to the fertility of the quarry, the way it gives birth to these enormous blocks. What is certain is that the Stone of the Pregnant Woman is one of the largest worked stones in the world, a monolith roughly 1,000 tons in mass, larger than any stone the Romans ever moved, larger than the trilithon blocks that form the foundation of the Temple of Jupiter at Baalbek, larger even than the unfinished obelisk of Aswan, and it never moved. Like the unfinished obelisk, the Stone of the Pregnant Woman was rough cut from the quarry face, and then abandoned. Unlike the unfinished obelisk, there is no visible crack, no obvious flaw, no clear explanation for why the work stopped. The Romans simply cut the stone free on 3 sides, prepared it for extraction, and then nothing. They walked away. They left 1,000 tons of perfectly good limestone lying in the quarry, and they never came back. Why? We do not know. Perhaps the stone was cut for a building project that was never completed. Perhaps the engineers calculated the logistics of transport and realized they had exceeded their capabilities. Perhaps the empire was distracted by wars or economic crises or changes in political leadership, and the quarry workers were reassigned to other projects. What we know is that the Romans, like the Egyptians, could rough-cut stones of extraordinary size. They could shape them. They could plan for them. But moving them was another matter. Moving them required infrastructure that may not have existed, labour forces that may not have been available, engineering solutions that may not have been invented. The stone of the pregnant woman tells us that even Rome had limits. Even the empire that built aqueducts and roads, and the Colosseum, even the civilization that moved the Lateran obelisk across the Mediterranean, even the engineers who had inherited 1,000 years of Egyptian knowledge, even they could quarry stones they could not move. The quarrying was solved, the technology was adequate, the labour was available, but the transport remained a problem, and the transport remained a problem because the stones were simply too heavy. This is the riddle at the heart of our documentary. Not, how did they carve the stones? We know how they carved them. Not, how did they shape them? We know how they shaped them. The riddle is, how did they move them? How did they transport hundreds of tons of dead weight from quarry to building site, sometimes across rivers, sometimes across deserts, sometimes across the Mediterranean Sea? And more than that, how did they lift them? How did they take a stone that weighed as much as a locomotive and raise it from horizontal to vertical, holding it steady against the tug of gravity while they slid the pedestal beneath it and locked it into place? The quarry marks tell us everything about extraction. They tell us about the dolerite pounders and the red ochre guidelines, and the organised gangs of workers who spent months or years freeing a single block from the living bedrock. The quarry marks are a complete record, a textbook, a manual of ancient technique. But the quarry marks tell us nothing about what happened next. The stones that made it out of the quarry erased their own transit. They arrived at their destinations clean and polished, and inscribed with the names of gods and kings, and they told us nothing about the journey. And the stones that did not make it out of the quarry, the unfinished obelisk, the stone of the pregnant woman, never began the journey at all. We are left with questions. We are left with the weight of unanswered things. We are left with stones that are still asking, after 3,000 years, after 5,000 years, after all the empires and all the collapses and all the archaeology and all the engineering analysis, we are left with stones that are still asking how. The sun sets over Aswan. The shadows lengthen across the quarry floor. The unfinished obelisk catches the last light, and for a moment, if you stand at the right angle, you can almost see what it would have looked like. The needle of pink granite rising against the desert sky. The tallest obelisk ever erected. The crowning achievement of a woman pharaoh who dared to rule in her own name. You can almost see it. But you cannot because it is not there. The crack saw to that. The flaw in the stone, the weakness hidden in the crystal structure, the moment when thousands of hours of labour came to nothing. The crack is still there, running through the granite like a sentence that was never finished, a thought that was never completed, a question that was never answered. How do you move a mountain? The Egyptians knew, the Axumites knew, the Romans knew, and we have forgotten. The forgetting began slowly, the way all great knowledge fades, not in a single catastrophic moment, but in the quiet accumulation of years, the deaths of master engineers, the burning of libraries, the collapse of empires that had once commanded the labour of nations. What remained were the stones themselves, standing or fallen, and the question they continued to pose to every generation that looked upon them and wondered. Let us begin with what we know about movement. Let us begin with the simplest possible scenario. A block of stone, a flat surface, and the problem of making one move across the other. Friction is the enemy. Every engineer who's ever contemplated moving a massive object understands this at a cellular level. The coefficient of friction between granite and sand, between limestone and mud, between any stone and any surface. This is the number that determines everything. Reduce friction, and you reduce the force required. Reduce the force required, and you reduce the number of men, the number of ropes, the number of animals, the number of days. The entire history of ancient megalithic transport can be understood as a war against friction, a campaign fought with lubricants and rollers and sledges and roads, a battle in which the enemy was physics itself and the weapons were ingenuity and sweat. The sledge is the oldest solution, a wooden platform beneath the stone, runners that slide rather than drag, a surface that can be prepared and smoothed and lubricated. The tomb of Jehuti-Hotep at Deir el-Bersha, dating to approximately 1900 BCE, shows us exactly what this looked like: a colossal seated statue, estimated at 60 tons, being pulled on a sledge by 172 men arranged in 4 rows. At the front of the sledge, a single figure pours liquid from a jar onto the path ahead. For a century, scholars assumed this was ritual, a libation to the gods, a symbolic act of purification. They were wrong. The liquid was lubricant. Water, or perhaps oil, poured onto the sand to reduce the friction coefficient, to make the sledge glide rather than grind, to transform an impossible task into merely an extremely difficult one. Modern experiments have confirmed this. Wet sand compacts and stiffens, creating a firmer surface. The water binds the grains together, prevents them from piling up in front of the sledge runners, reduces the dragging force by nearly half. The physics are sound. The method works. At small scales, it works beautifully. But the unfinished obelisk was not small scale. The Lateran obelisk was not small scale. The great stela of Axum was not small scale. And this is where the mathematics become uncomfortable. Mark Lehner, the American archaeologist who has spent decades studying the construction methods of the Giza Plateau, successfully employed sledge technology in his experimental work. When his team constructed a small pyramid, 18 feet tall, they used sledges and ramps and organised labour and all the techniques depicted in ancient tomb paintings, and they proved that the methods worked. The Egyptians had not possessed secret knowledge or lost technology or alien assistance. They had possessed understanding of friction and leverage and the patient application of human muscle, and that had been enough. But there is a problem of scaling. When you double the size of a stone, you do not double its weight. You increase it by a factor of 8, because weight scales with volume, and volume scales with the cube of the linear dimensions. A block twice as long, twice as wide, and twice as tall weighs 8 times as much. The relationship is not linear, it is exponential. And exponential relationships are unforgiving. Consider the arithmetic. A 2-ton block can be moved by a team of strong men on a prepared surface. The experiments have proven this. 12 men, perhaps, on wet sand with a well-made sledge and good ropes. The numbers are reasonable. The logistics are manageable. You could organise such a team in an afternoon, feed them from a village granary, house them in temporary shelters near the quarry. It is work, but it is not impossible work. Now consider 500 tons, not 2 tons but 500. Not a block the size of a large coffin, but a monolith the size of a building. If the relationship were linear, you would simply need 250 times as many men, 3,000 workers perhaps, which is a substantial labour force but not an inconceivable one. Empires have commanded larger armies. Pharaohs have conscripted greater multitudes. 3,000 men is a logistics problem, not an impossibility. But the relationship is not linear, because friction does not scale linearly with weight. The heavier the object, the more deeply it presses into the surface beneath it. The more deeply it presses, the more the surface deforms. The more the surface deforms, the harder the object is to move. A 2-ton block rests lightly on the sand. A 500-ton obelisk crushes the sand beneath it, compacts it, sinks into it. The sledge that glided so easily under the smaller load buries itself under the larger one. The water that lubricated the path is squeezed out by the pressure. The friction coefficient rises. The force required rises faster than the weight. This is why the extrapolations become troubling. If 12 men moved 2 tons in the experiments, how many men would be required for 500 tons? Simple multiplication suggests 250 times 12, 3,000 men. But the physics suggest more. The surface effects suggest more. The practical difficulties of coordinating thousands of workers pulling on the same set of ropes, the problem of fitting that many human bodies into a space where they can all exert useful force, the challenge of synchronizing their efforts so that the force is applied smoothly rather than in destructive jerks. All of this suggests that the real number might be far higher than any simple calculation would indicate. And this is before we consider the road. A sledge requires a surface. Not just any surface, a prepared surface, a maintained surface, a surface that can bear the weight without collapsing, that can shed water without becoming mud, that can survive the passage of hundreds or thousands of tons without crumbling into ruts and potholes. The ancient Egyptians were masters of road construction. The causeways that led to the pyramid construction sites were engineering marvels in their own right. Compacted surfaces reinforced with limestone chips, drainage channels cut into the bedrock, gradients calculated to minimise the pulling force. These roads took years to build. They required almost as much labour as the monuments themselves. For short distances, this was manageable. The quarries at Giza were close to the construction sites, within a few kilometres at most. The granite quarries at Aswan were farther, but the Nile provided an alternative. You did not need to drag the stones all the way from Aswan to Thebes. You needed to drag them to the river's edge, load them onto boats, and let the current do the rest. The river changed everything. Water is a more forgiving medium than sand. The buoyancy principle, articulated by Archimedes but understood intuitively by every boat builder who ever lived, tells us that a floating object displaces its own weight in water. A 500-ton obelisk, properly loaded onto a sufficiently large barge, would displace 500 tons of water, and the water would push back, supporting the stone, bearing its weight, transforming the crushing immensity of dead granite into something that could be moved by oars and sails and the patient flow of the Nile itself. But sufficiently large is doing a great deal of work in that sentence. The Lateran obelisk, standing today in Rome near the Basilica of St. John Lateran, began its existence in Egypt. It was carved during the reign of Thutmose III, completed and erected by his grandson Thutmose IV at the temple complex of Karnak sometime around 1400 BCE. It weighs approximately 413 tons, not the heaviest obelisk ever moved, but heavy enough to pose profound engineering challenges. And it was moved not once but twice. First from the Aswan quarries to Karnak, a journey of some 200 kilometres down the Nile, and then, nearly 2,000 years later, from Karnak to Rome, a journey that required crossing the Mediterranean Sea. The Roman Emperor Constantius II ordered the obelisk transported to Rome in the middle of the 4th century of the Common Era. The logistics were staggering. A surviving text fragment from an earlier reign, that of Thutmose III, I'm perhaps describing the transport of an earlier obelisk, documents the specifications of an obelisk ship, approximately 63 metres in length, approximately 21 metres in width. These are not the dimensions of a normal vessel. These are the dimensions of a floating platform, a purpose-built transport that existed for no other reason than to carry stones too heavy for any ordinary craft. The Roman historian Ammianus Marcellinus, writing in the 4th century, described the transport of obelisks to Rome. His accounts confirm that the undertaking was considered extraordinary, even by the standards of an empire accustomed to extraordinary undertakings. It required 2 ships, not one but 2 massive vessels working in coordination, the obelisks suspended somehow between them or loaded across their combined decks. It required hundreds of oarsmen, teams of men whose only purpose was to provide the motive force that would push these groaning, overladen hulls across the wine-dark sea. The journey took months. The risks were immense. A storm, a miscalculation, a structural failure in either ship. Any of these could have sent the obelisk to the bottom of the Mediterranean, lost forever beneath the waves. They succeeded. The obelisk reached Rome. Constantius II erected it in the Circus Maximus, where it would stand for over 1,000 years before being moved again, in 1588, to its current location. The survival of the Lateran obelisk is itself a kind of miracle, a testament to the engineering capabilities of at least 2 ancient civilizations and the determination of emperors who considered the movement of 500 tons of granite a fitting symbol of their power. But the Lateran obelisk had the Nile, it had the Mediterranean, it had water, which meant buoyancy, which meant that the crushing weight of the stone could be transformed into a displacement problem, a flotation problem, a problem of building ships large enough rather than pulling sledges hard enough. Axum had no river. The steely fields of ancient Axum in what is now northern Ethiopia contain some of the most remarkable monolithic structures in the ancient world. The tallest standing stela reaches approximately 24 metres into the sky. The largest stela ever erected, or rather ever attempted to be erected, stood 33 metres tall and weighed approximately 520 tons. It fell during installation and shattered, and its broken pieces still lie where they came to rest, a permanent monument to the catastrophic failure that marked the end of Axumite megalithic ambition. But before the fall came the transport. The quarries that produced the Aksumet stele are located on a ridge approximately 4 kilometers from the stele field. 4 kilometers of mountainous Ethiopian terrain, with no navigable waterway, no convenient riverine highway that could transform the problem from one of dragging to one of floating. The stele had to travel overland down slopes and across valleys, through a landscape that offered no natural assistance. This is where the evidence becomes strange. David Phillipson, the British archaeologist and historian who devoted decades to studying the Aksumet civilization, searched for evidence of how this transport was accomplished. He looked for wheel ruts, the grooves that would be worn into stone or compacted earth by the repeated passage of heavy-wheeled vehicles. He found none. He looked for prepared road surfaces, the causeways and construction paths that the Egyptians had built with such care. He found none that could be definitively associated with stele transport. He examined Aksumite art, the carved reliefs and decorations that adorned the stele themselves and the other monuments of the civilization. He found no depictions of wheels. This absence is significant. The wheel was known in the ancient world. The Egyptians used wheels, though perhaps not for the heaviest transport. The Romans used wheels. The civilizations of Mesopotamia had been using wheels for millennia by the time the Aksumite stele were erected. If the Aksumites had used wheeled vehicles to transport their monoliths, we would expect to find some evidence, artistic, archaeological, geological. The fact that we find nothing suggests that they did not use wheels. But if not wheels, then what? The sledge remains possible. Sledges do not leave the same distinctive traces that wheels do. A sledge dragged across earth packs the surface down rather than cutting grooves into it. A sledge route once abandoned might be reclaimed by vegetation, eroded by rain, transformed back into ordinary terrain within a few generations. The absence of evidence is not evidence of absence, but the absence of any depiction, any written record, any archaeological feature that definitively explains Aksumite transport methods, this absence is troubling. We are left with a 500-ton monolith that somehow travelled 4 kilometres from quarry to erection site across terrain that offered no hydraulic advantages, leaving behind no clear record of how the journey was accomplished. The Egyptians documented their methods in tomb paintings and temple reliefs. The Romans wrote treatises on engineering. The Aksumites left us the stele themselves and almost nothing else. We know they succeeded. The standing stele are proof that transport was accomplished, that erection was achieved, that the engineering problems were solved. We do not know how they succeeded. We can only look at the results and work backward, inferring causes from effects, reconstructing methods from outcomes. Axum remains, logistically, the most inexplicable of them all, but transport is only half the problem. Moving a 500-ton monolith from quarry to site is an extraordinary achievement. Raising that monolith from horizontal to vertical, erecting it in the language of the engineers, is something else entirely. Consider the physics. A prone obelisk exerts its weight downward, distributed along its entire length. The ground bears this weight across a large surface area. The pressure at any given point is manageable. But the moment you begin to raise the obelisk, the moment you lift one end while the other remains grounded, everything changes. The entire weight of the stone concentrates at the pivot point, the end that is still touching the ground, the fulcrum around which the entire mass is rotating. The pressure at that point becomes immense. The stone crushes into the earth beneath it. The earth may give way, the stone may crack, and as the angle of elevation increases, so does the danger. A prone obelisk cannot fall. A vertical obelisk is stable, balanced on its base, its centre of gravity directly above its point of support. But an obelisk at 45 degrees, an obelisk at 60 degrees, an obelisk at any angle between horizontal and vertical. This is an obelisk in crisis, an obelisk fighting against gravity, an obelisk waiting to fall. If the ropes slip, it falls. If the support structure fails, it falls. If the workers lose coordination, if the pivot point crumbles, if the stone itself cracks under the concentrated stress, it falls. And when 500 tons of stone falls from even a modest height, the energy released is catastrophic. The impact shatters the monolith. Decades of quarrying, months of transport, years of planning, all of it destroyed in a single instant of failure. This is what happened at Aksum. The great stele, 33 meters tall, 520 tons of carved Nephilim syenite, the largest monolith ever worked by human hands, it fell during erection. The evidence suggests that it never stood at all, that it reached its intended site, that the erection process began, and that something went wrong. A rope broke. A lever slipped. The sand beneath the pivot point gave way. We do not know what failed. We know only that it failed, and that the greatest of the Aksumite stelae has lain broken ever since, a permanent memorial to the catastrophic risks of the erection moment. How did the ancients mitigate this risk? How did they raise stones that weighed as much as small ships, holding them steady against the pull of gravity while they manoeuvred them into position? The tilting ramp is one answer. The German engineer Uwe Hölscher, working at Karnak in the early 20th century, proposed a method that would use the ramp not only for transport but for erection. The obelisk would be hauled up the ramp on its sledge, its base pointing upward toward the sky. At the top of the ramp, a trench would be waiting, a carefully prepared hole, lined with sand sized to receive the base of the obelisk. The obelisk would be slid forward until its base tipped over the edge and began to descend into the trench. Gravity would do the rest, pulling the base down while the shaft rotated upward, transforming the prone monolith into a vertical needle. The physics are elegant. The ramp provides controlled descent. The trench provides a socket for the base. The weight of the obelisk itself provides the motive force. Once the tipping point is passed, once the centre of gravity shifts past the edge of the trench, the obelisk will fall into position, with the inevitability of a pendulum returning to rest. But elegance on paper is not the same as success in practice. The stresses on the base of the obelisk during this manoeuvre would be immense. The moment of tipping would be the moment of maximum danger, and the tolerances would be unforgiving. The trench would have to be exactly the right size, exactly the right depth, exactly the right angle, or the obelisk would not seat properly, would not stand vertically, would not achieve the perfect alignment that these monuments demand. Franz Lohner, an engineer who has devoted considerable effort to reconstructing ancient Egyptian construction methods, proposed an alternative, the A-frame and counterweight system. In this model, the obelisk would not be raised by sliding it over an edge, but by rotating it upward using a lever system. An A-frame of timber would be constructed at the erection site, tall enough to accommodate the full length of the obelisk. Ropes would connect the shaft of the obelisk to the apex of the A-frame, run over pulleys or greased rollers, and attach to counterweights or teams of workers on the other side. As the counterweights descended or the workers pulled, the obelisk would rotate upward, rising from horizontal toward vertical in a controlled arc. This method reduces the stress at the pivot point by distributing the force more evenly. It allows for precise control over the rate of rotation. It provides a mechanical advantage that could make the raising of even an enormous monolith feasible with available labour forces, but it requires an A-frame structure strong enough to bear the stresses involved, ropes capable of handling the loads, pulleys or rollers that will not seize under pressure, and a coordination of effort that would challenge any modern construction team. And then there is the sand drain method. An inscription from ancient Luxor, fragmentary but suggestive, contains a phrase that has fascinated Egyptologists for generations. Empty the space that has been filled with sand beneath the monument of thy Lord. This single sentence implies a technique that might explain how the most massive obelisks were erected. A technique that uses sand not as a surface to drag across, but as a medium to be removed. Picture the process. A pit is dug at the erection site, large and deep enough to accommodate the base of the obelisk with room to spare. The pit is filled with sand. Tons of sand, carefully controlled, precisely measured. The obelisk is positioned on top of the sand-filled pit, its base extending over the edge, its shaft supported by whatever combination of ramps and scaffolding the builders have devised. Then, slowly, the sand is allowed to drain from the pit. Holes are opened at the base. Workers remove sand by hand or by basket. The level of sand in the pit drops, and as it drops, the obelisk descends. The beauty of this method is the control it provides. Sand can be removed grain by grain if necessary. The rate of descent can be precisely managed. If something goes wrong, if the obelisk begins to tip in the wrong direction, if a stress fracture appears, if the alignment drifts off true, the process can be halted. More sand can be added. Adjustments can be made. The obelisk can be raised slightly and repositioned. The sand acts as a buffer, a shock absorber, a medium that forgives minor errors and allows for correction. The evidence from Karnak supports this interpretation. Excavations in the 1990s revealed the remains of what appears to be an erection pit, a massive structure of mud brick shaped like a funnel, sized to accommodate the base of an obelisk. The funnel shape would have directed the sand towards central drain points, making removal efficient. The mud brick construction would have been strong enough to withstand the pressures involved, yet easy enough to demolish once the obelisk was standing and the pit was no longer needed. This is the best physical evidence we have for ancient erection methods. It does not prove that the sand drain technique was used. Absence of alternative evidence is not proof of the alternative's non-use, but it strongly suggests that the Egyptians had developed a sophisticated method for the most dangerous phase of obelisk installation, a method that turned the erection crisis into a controlled engineering procedure. Modern experimenters have confirmed that the basic principles work. Rick Brown, Mark Lehner and their colleagues have successfully erected smaller obelisks using methods consistent with ancient techniques. Given enough time and enough people, using only technology available to the ancient Egyptians, erection is achievable. The problem is not impossibility. The problem is risk. The margin for error at full scale, with 500 tons of stone and the fate of years of labour hanging in the balance, remains terrifyingly narrow. And still, the question returns, how much of this is reconstruction, and how much is invention? We have the funnel pit at Karnak. We have the fragmentary inscription at Luxor. We have the tomb paintings and the scattered textual references and the standing obelisks themselves, which prove that success was achieved. But we do not have a manual. We do not have a step-by-step description from an ancient engineer explaining exactly how it was done. We are working from outcomes backward to methods, and this process inevitably involves speculation. The Axumites did not even leave us that much. The Great Stela fell, and we do not know why it fell, which means we do not know how the Axumites intended to prevent it from falling. They must have had a method. They successfully erected the other stelae, the ones that still stand. They achieved erection at a scale that would challenge modern cranes. But their method is lost, vanished with the scribes and engineers who never recorded it, erased by the centuries that passed between their civilization and ours. And then there is Rome. In September of 1586, the architect and engineer Domenico Fontana faced a challenge that would define his career and test the limits of Renaissance engineering, moving the Vatican obelisk. The obelisk had stood in the same location since the reign of the Roman Emperor Caligula, who had transported it from Egypt in the 1st century of the Common Era. It weighed, by various estimates, somewhere between 320 and 327 tons. It had stood for 15 centuries on Roman soil, and now Pope Sixtus V wanted it moved. The new location was only a few hundred meters away, a trivial distance by the standards of ancient Egyptian transport, a journey the original builders would have considered barely worthy of mention. But Fontana was not an ancient Egyptian. He did not have access to the labour forces of a pharaoh's court. He did not have the institutional knowledge that had been accumulated over 3,000 years of pyramid and temple construction. He had to work from first principles, reinventing techniques that had been lost with the fall of Rome, solving problems that the ancients had solved and he had never learned. The operation required 13 months of preparation. Fontana designed a system of levers and winches, a network of ropes and pulleys, a scaffolding structure that would support the obelisk during its journey. He assembled a workforce of 800 men, other sources say 900, and 160 horses. He constructed 45 winches, massive wooden drums around which the ropes would be wound, each winch operated by teams of men and animals working in coordination. The lifting began on the morning of September the 10th. The process would take the entire day. Every stage had to be perfect. Every rope had to hold. Every winch had to turn at the correct speed, synchronized with all the others, maintaining even tension across the entire system. If one rope slipped while the others held firm, the obelisk would twist. If one winch turned too fast or too slow, the load would shift. If any element of the system failed, any rope, any pulley, any anchor point, the obelisk would fall, and 300 tons of ancient granite would shatter against the Roman pavement. The Pope had decreed absolute silence. This was not theatre. It was engineering necessity. The workers needed to hear the commands of their supervisors. They needed to hear the trumpets that signalled when to pull, and the bells that signalled when to stop. Any unauthorised noise, any shout or cry that might be mistaken for a command, could trigger a disastrous miscommunication. Sixtus V had threatened death to anyone who broke the silence. Whether this threat was enforceable is beside the point. The point was that everyone understood the stakes. Everyone understood that a moment of chaos, a moment of confusion, could destroy an irreplaceable artifact and kill dozens of men. 13 hours into the operation, the ropes began to overheat. Friction again, the enemy that haunts every megalithic undertaking. The ropes were stretched to their limits, under tensions that approached the breaking point, sliding through pulleys, winding around winches. The friction generated heat. The heat dried the fibres of the ropes. The dry fibres became brittle. The brittle fibres began to fray. A sailor named Benedetto Bresca saw it happening. He understood what he was seeing, understood that the ropes were on the verge of failure, understood that within minutes the entire system might collapse. And he understood that the Pope had forbidden speech on pain of death. He shouted anyway, "Acqua alle funi," water on the ropes. The cry broke the silence. It violated the direct order of the Pope himself, but it saved the obelisk. Workers rushed to pour water over the ropes, cooling them, restoring their flexibility, allowing the operation to continue. The obelisk reached its new position. It was lowered onto its pedestal. It was secured. The operation was complete. Bresca was not executed. The Pope, recognizing that the sailor had saved the obelisk through an act of courage that risked his own life, pardoned him on the spot. More than that, he rewarded him. Bresca and his family were granted the privilege of providing palms for Vatican religious holidays, a commercial right that would benefit them for generations. The man who broke the silence became a hero, and the story of his shout has been told for more than 400 years. Fontana documented everything. In 1590, he published his treatise Della Transportazione dell'Obelisco Vaticano, a detailed account of the engineering methods he had employed, a technical manual that preserved for posterity the knowledge he had gained through trial and error. The book includes illustrations of the winches and scaffolding, diagrams of the rope arrangements, calculations of forces and tensions. It is the most complete record we have of how a Renaissance engineer solved the problem of moving a monolith. And here is what the record tells us. It took everything Fontana had: 800 or 900 men, more than 160 horses, 45 winches, 13 months of preparation and 13 hours of execution. Iron hardware and block and tackle systems that the ancient Egyptians did not possess. All of this for a stone that weighed at most 330 tons. The Lateran obelisk weighs over 400 tons. The Great Stela of Axum weighed over 500. The unfinished obelisk, had it been completed and extracted, would have weighed over 1,100 tons, more than 3 times the mass that brought Fontana's operation to the edge of catastrophe. What did the ancients use? If Renaissance engineering, with all its iron and all its winches and all its coordinated labour, could barely manage 300 tons, what did the pharaohs use for 400? What did the Axumites use for 500? What technology existed in the Bronze Age that could accomplish what Renaissance technology could barely achieve? The answer, whatever it is, has been lost. The methods that moved the Lateran obelisk from Aswan to Karnak and from Karnak to Rome, the methods that raised the stelae of Axum on a ridge 4 kilometers from their quarry, the methods that would have transported the unfinished obelisk if it had not cracked, these methods are gone. We have the stones. We have the questions. We do not have the answers. In the 1990s, when the Italian government agreed to return the Axum obelisk that had been looted by Mussolini's forces in 1937, a new engineering problem emerged. The obelisk had been cut into 3 pieces for transport to Rome, where it had stood near the Circus Maximus for more than half a century. Now those 3 pieces needed to be flown back to Ethiopia, transported not by ship but by cargo aircraft, the largest available, aircraft designed to carry the heaviest loads that modern logistics required. A consortium of engineering firms, including the Italian company CGT, conducted feasibility studies. They examined the weight of the sections, approximately 160 tons for the largest piece. They calculated the lifting capacity of available cranes. They assessed the ground conditions at the erection site. Their conclusion was sobering. No single crane commercially available at the time could lift the sections without extensive ground reinforcement. The soil at the Axum Stele field, the same soil that had supported the erection of monoliths 5 times heavier than the returning sections, could not bear the concentrated load that a modern crane would impose. The outriggers, the stabilizing feet that allow a crane to operate without tipping, would sink into the earth. The crane would become unstable, the lift would fail. The ancient Axumites had erected a 500-ton monolith on this same ground. They had done it without cranes, without outriggers, without reinforced concrete foundations, and modern engineers, with all the technology of the 20th century at their command, had to perform extensive site preparation before they could handle sections weighing less than a third of the ancient whole. The obelisk was eventually re-erected. The ground was reinforced, the cranes were deployed, the sections were stacked and joined, and the monument restored. But the process required years of planning, millions of dollars, and engineering resources that would have been unimaginable to the workers who originally quarried and raised the stone. And still the ancient method remains unknown. Still the question persists. Still the stelae stand, or lie broken, offering no explanation for their own existence. The engineers who raised them left no treatise, no diagram, no fontana to document their accomplishment. They left only the stones themselves, and the stones have never spoken, and the stones have never spoken. But they have been asked. Again and again, in languages the original builders would never have recognised, the questions have been posed to granite and basalt and the stubborn red rock of Aswan. Modern engineers, armed with calculators and stress load tables and computer simulations, have stood before these monuments and asked, how? The stones offer no reply. They simply wait, as they have waited for millennia, their surfaces worn by wind and rain, and the touch of countless hands, their mass undiminished, their secrets intact. In the early years of the 21st century, a new kind of question was posed, not in words but in action. If the ancient methods could not be reconstructed from texts or images, perhaps they could be reconstructed from experiment. Perhaps by attempting to replicate the feats of the ancients using only the tools and techniques available to them, modern researchers could reverse engineer the lost knowledge. It was an elegant hypothesis. It was also, as events would demonstrate, an exercise in humility. The experiments took place near the Giza Plateau, within sight of the pyramids themselves, under the direction of men who had spent their careers studying the construction methods of ancient Egypt. Mark Lehner, the American archaeologist who had devoted decades to mapping and analysing the Giza complex, joined forces with Roger Hopkins, a professional stonemason whose hands knew the weight and grain of rock in a way that academic study could never fully convey. Together they assembled a team, labourers, engineers, cameramen for the documentary crews that would record their efforts, and set out to answer a deceptively simple question. Could they raise an obelisk using only the methods available to the pharaohs? The obelisk they chose was modest by ancient standards, a replica carved from limestone rather than granite, weighing approximately 25 tons. This was a fraction of the mass of even the smaller Egyptian obelisks. The Flaminia obelisk in Rome, one of the lightest ancient Egyptian obelisks to survive, weighs over 200 tons. The Lateran obelisk, as we have seen, weighs over 400. The replica that Lehner and Hopkins proposed to raise was by comparison almost trivially small, a single block of the kind that formed the lower courses of the Great Pyramid, a mass that a modern crane could lift in seconds, almost as an afterthought. And yet the task proved extraordinarily difficult. The team experimented with various configurations. They constructed ramps and A-frames. They recruited labourers, dozens of men pulling on ropes, coordinating their efforts with the same kind of rhythmic chanting that tomb painting suggests the ancients may have used. They tested the sand drain technique, the method suggested by the inscription at Luxor, tilting the obelisk into position while workers beneath the turning point removed sand in carefully controlled quantities, allowing the stone to pivot slowly, its weight transferring from horizontal to vertical in a gradual precarious arc. The technique worked, in theory. In practice, it was terrifying. An obelisk, even a small one, is not a static object during erection. It is a dynamic system, a mass in motion, subject to forces that shift and multiply as the angle changes. When the stone is horizontal, its weight is distributed along its entire length, pressing down evenly on the supporting surface. As it tilts, that weight begins to concentrate. The base digs into whatever material it rests upon. The tip rises, first slowly, then with increasing momentum as the angle steepens. And at a certain critical point, somewhere between 45 and 60 degrees, depending on the proportions of the stone and the friction of the pivot surface, the obelisk reaches an inflection. The mass that was resisting the lift begins to assist it. Gravity, which had been an obstacle, becomes an ally. The stone wants to stand up. But this is also the moment of maximum danger. At the critical angle, The forces acting on the obelisk are enormous and unstable. A small miscalculation, too much sand removed on one side, too little on the other, a rope slipping, a timber cracking, and the stone will not pivot smoothly into the vertical. It will fall, it will twist, it will shatter into fragments, crushing anyone unfortunate enough to be in its path. The team led by Lena and Hopkins experienced this danger firsthand. Their 25-ton replica, during the critical pivot phase, became unstable. The ropes strained. The A-frame groaned under loads it was not quite designed to handle. For long, tense hours, the stone hung at an angle, neither rising nor falling, while the team recalculated, readjusted, and tried again. The full effort consumed 16 days. 16 days of labour, 16 days of coordination, 16 days of near misses and incremental progress. 16 days for 25 tons. The mathematics are not complicated, but they are merciless. If a team of dedicated modern workers, led by experts who had studied ancient methods for decades, required 16 days to raise 25 tons, how long would it have taken the ancients to raise 400, 500, 1100? The scaling is not linear. The problems do not simply multiply, they compound. A 500-ton obelisk is not merely 20 times harder to raise than a 25-ton replica. It is qualitatively different, a challenge that exists in a different category entirely, requiring solutions that the experiments at Giza could not even gesture toward. And this is the point at which the documentary must pause and acknowledge an uncomfortable truth. The experiment succeeded, in a limited sense. A small obelisk was raised. Ancient methods were demonstrated to be viable, at least at modest scales. But the experiments also failed, in a deeper sense. They failed to answer the central question. They failed to show how the ancients could have raised the truly massive stones, the Lateran, the great steeler of Axum, the unfinished obelisk that never left its quarry. The gap between what was demonstrated and what was achieved in antiquity remained unbridged, and the experiments, rather than closing that gap, had the paradoxical effect of widening it. By showing how difficult it was to raise 25 tons, they made the raising of 500 tons seem not merely impressive but almost miraculous. The word should be used carefully. Miracle implies the supernatural, and there is nothing supernatural about the obelisks. They are rock. They obey physics. They were raised by human beings using human tools and human labour. The ancients did not possess levitation technology or anti-gravity devices or assistance from extraterrestrial visitors. These fantasies, popular in certain corners of modern culture, are not merely wrong. They are insulting to the ingenuity and determination of the people who actually accomplished these feats. The builders of the obelisks were not aided by magic. They were engineers, solving engineering problems, with brilliance and courage and a tolerance for risk that modern safety protocols would never permit. But the methods they used have been lost, and in their absence, even the word engineering begins to feel inadequate. Consider what was happening in Ethiopia while the experiments at Giza were underway. The Axum obelisk, the stela looted by Mussolini's forces in 1937, erected in Rome as a trophy of fascist conquest, was finally returning home. The process had been negotiated for years. The Italian government, acknowledging the injustice of the original seizure, had agreed to return the monument. A consortium of engineering firms had been assembled. The logistics had been planned with military precision. The obelisk, as it stood in Rome, was in 3 sections. The Italian engineers who had transported it in 1937 had cut it apart to make shipping possible. A practical decision that would prove ironic in the decades to come, since the cutting had damaged the stone and complicated the eventual restoration. Each section weighed approximately 160 tons. The total weight, fully assembled, would be close to 500 tons, roughly equivalent to the great stela that still lay shattered in the Axum stela field, the monument that had fallen during its original erection attempt some 17 centuries earlier. The return journey required aircraft capable of carrying loads that no cargo plane had been designed for. The Antonov An-124, one of the largest cargo aircraft ever built, was pressed into service. Multiple flights were necessary. The logistics were staggering. The route from Rome to Axum, the coordination of ground transport at both ends, the construction of temporary roads rated for the extreme axle loads that the transport vehicles would impose. And then came the re-erection. The site at Axum presented challenges that the Italian engineers had anticipated, but could not fully prepare for. The steely field sits on a ridge above the town, a plateau of compressed earth and buried archaeology. The ground that had supported the erection of monoliths in antiquity was not uniform. Centuries of weathering and human activity had altered its composition. More critically, the ground had never been subjected to the concentrated loads that modern lifting equipment would impose. A crane, when it lifts a heavy object, does not simply raise the load. It transfers the load's weight, plus the weight of the crane's own structure, plus the dynamic forces generated by the lifting action, down through its base and into the earth. The outriggers, those extending feet that stabilize the crane and prevent it from tipping, act as pressure points. They concentrate enormous force into relatively small areas, and that concentrated force, on ground that is not adequately prepared, causes sinking. The outriggers dig in, the crane tilts, the load swings, and if the tilt is not corrected immediately, the entire system, crane, load, operators, can collapse. The engineers responsible for the Axum re-erection understood this danger. Their feasibility studies had identified the soil conditions as a critical variable. They knew that no single crane commercially available could perform the lift without extensive ground reinforcement. Even the largest mobile cranes, machines capable of lifting 500 tons or more under ideal conditions, required a foundation that the Axum site did not naturally provide. The solution was engineering on a massive scale. Temporary roads were constructed, not merely graded but reinforced, capable of supporting axle loads of 100 tons, far heavier than any truck that normally travels Ethiopian highways. The ground at the erection site was excavated, stabilized, and in some areas replaced entirely with compacted material that could bear the concentrated pressures the cranes would impose. Concrete foundations were poured, steel mats were laid. The site was transformed from an ancient monument field into something resembling an industrial construction zone. 2 Liebherr LTM 1500 mobile cranes were brought in, machines at the upper end of commercial lifting capacity, each capable of raising approximately 500 tons under optimal conditions. But the conditions at Axum were not optimal. The sections of the obelisk, while lighter than the full monument, were awkwardly shaped. Tall and narrow, prone to swinging, difficult to control, the lift required not raw power but precision, and precision with objects weighing 160 tons is a matter of millimeters and seconds. The cranes worked in tandem. The lifts were choreographed with the care of a surgical operation, except that in surgery, a mistake costs 1 life, while a mistake here could have killed everyone on site. The sequence of operations stretched over multiple days. Each section was raised, positioned, aligned, and set in place, while engineers monitored stress loads and ground conditions and wind speeds and 100 other variables that could turn routine into disaster. The operation succeeded. The Axum obelisk stands once more on Ethiopian soil, restored to the steely field where it was originally erected, a monument reclaimed after decades of displacement. The engineering was flawless. The coordination was exemplary. The cranes performed precisely as their specifications promised. And yet, the cranes lifted 160 tons per section. The ancient Axumites, 17 centuries earlier, had raised the entire monument, all 500 tons of it, in a single piece. They had done it without cranes, without reinforced foundations, without steel mats or concrete pads or temporary roads rated for axle loads that would sink a modern semi-truck into the earth. They had done it on the same ridge, the same soil, the same site that had required years of preparation and millions of dollars before modern engineers could manage 1/3 of the weight. How? The question is not rhetorical. It is not a device to generate mystery or to suggest that the ancients possessed capabilities beyond human understanding. It is a genuine, honest, unanswered question. How did they do it? What technique, what combination of levers and ropes and rollers and human coordination allowed them to accomplish what modern cranes, at the very edge of their capacity, could barely replicate in diminished form? The experiments near Giza had shown that ancient methods were viable for small stones. The re-erection at Axum had shown that modern methods could handle medium stones. But the great stones, the fallen stela of Axum, the Lateran obelisk, the unfinished obelisk of Aswan, these remained beyond both ancient demonstration and modern replication. The ancients had raised them. We have not. And the honest assessment of modern engineering is that we probably could not with period-accurate tools and methods, not without the cranes and diesel engines and reinforced concrete that the ancients did not possess. This is the vertiginous moment. This is where the documentary arrives at its true climax, not in spectacle, but in silence. The realization is not that the ancients were superhuman, but that they were human in ways we have not fully understood, that their knowledge of stone and weight and force and coordination exceeded what we have been able to recover from the archaeological record. The methods are not merely unknown, they may be unknowable. The practitioners are dead. The tradition is broken, and the stones, for all their mass, are lighter than the silence that surrounds them. There is one more quarry to visit, one more stone to stand before. Baalbek lies in the Bekaa Valley of Lebanon, a site of ruins so massive that Roman engineers, the same Romans who transported the Lateran obelisk across the Mediterranean, looked upon the foundations and marvelled. The Temple of Jupiter, built in the 1st century of the Common Era, rests on a platform that includes some of the largest quarried stones ever moved by human hands. 3 blocks in the western foundation, known as the trilithon, weigh approximately 800 tons each. They were transported from a quarry several hundred meters away, raised 20 feet into the air, and fitted into place with a precision that leaves no visible gap, no mortar, no evidence of how the positioning was achieved. 800 tons, raised 20 feet, fitted to tolerances measured in fractions of an inch, and in the quarry itself 3 more stones remain. The Stone of the Pregnant Woman, so named for legends that attribute its presence to the work of a pregnant jinn or goddess, lies where it was abandoned, still attached to the bedrock at one end, never fully freed. Its weight has been estimated at approximately 900 tons. It is oriented on a slope, as if it were being prepared for transport downhill toward the temple complex, but it never moved. The work stopped. The stone remained. For centuries, it was considered the largest worked monolith on Earth. Then, in the 1990s, excavations beneath and beside it revealed another stone, larger still. This block, sometimes called the Stone of the South, weighs approximately 1,242 tons, more than the unfinished obelisk of Aswan, more than anything the Egyptians are known to have attempted. It too lies in the quarry, fully shaped, fully freed from the bedrock, but never transported, never raised, never fitted into position beside the trilithon. And in 2014, a German archaeological team from the German Archaeological Institute, conducting systematic excavations of the quarry, discovered a 3rd stone. This block, buried beneath centuries of accumulated debris, weighs approximately 1,500 tons. It may be the largest worked stone ever identified anywhere on Earth. 1,500 tons. The weight of 10 fully loaded Boeing 747 aircraft. The weight of 3,000 draft horses. The weight of a small naval vessel carved from solid rock, shaped by human hands, lying in a quarry in the mountains of Lebanon, waiting for transport that never came. Why was it abandoned? Jean-Pierre Adam, the French architect and engineer who conducted detailed studies of ancient construction methods, offered a hypothesis in the 1970s. Adam calculated that the transport of massive blocks was theoretically possible using ancient methods: wooden rollers, capstans, pulleys, coordinated labour. His estimates suggested that a block weighing approximately 800 tons could be moved by 500 workers operating 40 capstans, hauling the stone up a prepared ramp with a gradient of perhaps 20%. The numbers were plausible, the physics worked. The Romans, Adam suggested, had the capability to move the trilithon stones, but the quarry stones were larger, much larger. Perhaps, Adam suggested, the Romans who worked the Baalbek quarry reached a limit. Perhaps they quarried the Stone of the Pregnant Woman and the Stone of the South, and the great block discovered in 2014 with the intention of moving them, and then discovered, through calculation or failed experiment, that the transport problem was unsolvable. Perhaps they looked at the numbers, looked at the stones, looked at the distance to the temple, and the gradient of the slope and the friction of the rollers, and concluded that these blocks were simply too heavy, that the ambition had exceeded the possible, that the only option was to leave the stones where they lay and pretend, for the honour of the engineering corps, that the project had been abandoned for other reasons. If so, the stones are not monuments to failure, they are monuments to ambition. They represent not the limit of what the ancients could do, but the limit of what the ancients dared attempt. They mark the boundary where confidence ended and prudence began, the point at which even the most skilled engineers of the ancient world looked at a problem and admitted that it might be beyond them. But here the Ethiopian evidence complicates the story. The great stela of Aksum, the one that fell, the one that lies shattered in the stellar field, the monument that represented the largest single object the Aksumite civilization ever attempted to raise, weighs approximately 520 tons. It is smaller than the Baalbek quarry stones, but it was successfully transported from a quarry 4 kilometers away, across terrain that offered no river access, no obvious road network, no evidence of wheels or rollers, or any of the technology that the Romans possessed. The stone was moved. The stone was brought to the site. The stone was raised, or nearly raised. It fell during the erection attempt, but it reached the point of erection, it was tilted into position, it was within moments of standing when something failed and it crashed to the ground. The Aksumites, in other words, solved a transport problem that the Romans at Baalbek apparently could not. They moved 500 tons over 4 kilometers of Ethiopian highland terrain without any of the advantages that Roman engineering is thought to have possessed, and they left no record of how they did it. David Philipson, the British archaeologist who spent decades studying the Axum stele, searched for evidence of the transport method. He excavated the quarry. He surveyed the route. He looked for prepared roads, for roller tracks, for any trace of the infrastructure that such a transport would seem to require. He found nothing. The ground was undisturbed. The path was unimproved. The 500-ton stela had been moved somehow, without leaving any detectable trace of its passage. This is not mystery-mongering. This is archaeology confronting its own limits. The evidence that should exist does not exist. The explanations that should be obvious are not obvious. The methods that should be recoverable from the physical record have vanished, leaving only the stones themselves, stones too heavy to move by any method we can currently reconstruct, standing or fallen in fields and temples and quarries around the ancient world, testifying to knowledge that we have lost. And so the documentary returns at its end to where it began. The unfinished obelisk of Aswan lies in its trench, still bearing the red ochre marks that Reginald Engelbach recorded in 1922. The gang marks are visible, the signatures of the work crews, the boundaries of their daily progress, the evidence of organised labour operating with precision and coordination across the face of the granite. The technique is understood. The quarrying method has been reconstructed. We know how they shaped the stone. We know how they would have freed it from the bedrock if the crack had not appeared. What we do not know is how they would have moved it. 1,168 tons, 41 metres of solid granite. A mass so great that no crane currently in commercial operation could lift it. A length so extreme that transport by road would require curves and clearances that ancient infrastructure could never have provided. A problem so complex that even today, with all the engineering resources of the 21st century, no one has proposed a convincing, period-accurate solution. The obelisk lies in its quarry. It has lain there for 3,500 years. It was intended for Karnak, for a temple that Hatshepsut was building to honour the gods in her own glory. It would have been the largest single object ever raised by human hands. It would have been visible for miles across the Nile floodplain, a needle of red granite catching the morning sun, a monument to the power of a civilization that could move mountains. Instead, it is a monument to a question. The same question that hangs over the Lateran obelisk in Rome, the stelae of Axum, the trilithon of Baalbek, the quarry stones that never moved, the fallen monuments that lie broken in fields and temple courts across 3 continents. The question is not why they tried. The question is not what they hoped to achieve. The question is how. How did they move these stones? How did they raise them? What knowledge did they possess that we have lost? What techniques did they master that we cannot reconstruct? What combination of physics and labour and courage and coordination allowed them to accomplish feats that modern engineering regards with something close to awe? The stones do not answer. They have never answered. Perhaps they never will, but they remain. The unfinished obelisk remains in Aswan, the Lateran obelisk remains in Rome, the stelae remain at Axum, standing and fallen, whole and shattered, restored and abandoned. The granite endures, the basalt endures. The limestone of Baalbek, the syenite of Ethiopia, the red rock of the Aswan quarries. These materials do not decay on human timescales. They will outlast the civilizations that shaped them. They will outlast the languages in which the questions are asked. And perhaps that is the only answer the stones were ever meant to provide. Not a solution to a puzzle, not a method to be reconstructed, but a reminder that human beings, working at the edge of the possible, have always reached further than prudence would advise. A reminder that the monuments we raise are never only about the gods or the kings or the causes they commemorate. They are about the act of raising itself, the assertion that gravity can be defied, that mass can be moved, that the weight of the world can be lifted by hands and ropes, and the sheer refusal to accept limits. The abandoned stones are not failures. They are the outer markers of ambition. They show us how far the ancients were willing to go, how close they came to the impossible, how narrow the margin was between triumph and catastrophe. The unfinished obelisk cracked and was abandoned, but for a flaw in the granite it would have stood at Karnak, the largest monument of its kind, a record that might never have been broken. The great stela of Axum fell and shattered, but for a moment, a single moment in the 17th century of the Common Era, it was rising, it was tilting toward the vertical, it was about to stand. These are not stories of defeat, they are stories of reach, and so the documentary closes not with an answer but with an image. The Baalbek quarry at dusk, the light failing over the Beaker Valley, the mountains casting long shadows across the stones. The stone of the pregnant woman lies where it has lain for 2,000 years, half freed from the bedrock, oriented toward a temple it was never meant to join. Beside it, still partially buried, the great block that weighs 1,500 tons, the largest worked stone on earth, shaped by hands that left no record, abandoned for reasons that were never written down. The stones wait. They have waited for millennia. They will wait for millennia more. Somewhere in the silence between the questions and the stones there is knowledge, lost knowledge. Knowledge that moved mountains and raised monuments and accomplished feats that we can barely comprehend, let alone replicate. The men and women who possessed that knowledge are dust. Their methods died with them. Their treatises, if they ever existed, have not survived, but the stones remain. The stones remain, and that perhaps is enough. Not an answer, but a testament. Not a solution, but a challenge. The ancient builders reached the edge of the possible and sometimes stepped beyond it. They lifted weights that should not have been liftable. They raised monuments that should not have stood. They left us not a manual but a question, and the question, posed in granite and basalt in the red rock of Aswan, has outlasted every answer we have tried to give. Listen. The wind moves through the Baalbek quarry. The shadow of the mountains falls across the stone, and somewhere in the silence, the oldest question in the world is still waiting to be asked. How did they do it? The stones know. The stones have always known, and the stones have never said a word.